Hello everyone, we are Group 4, Harsh, Shreya and myself, Hema. For our NoSQL term paper topic, we have chosen Neo4j as our NoSQL database. In this presentation, we will be discussing some of its features and in the end, we will demonstrate our movie console application which is built using Neo4j. Looking at the roadmap for today's presentation, we will give a brief introduction on Neo4j, followed by a discussion on how data is stored in the database, then moving on to query processing and query optimization. We will also talk about important aspects of a database management system, such as indexing, constraints, and transaction management. We will demonstrate our application using some screenshots and conclude our presentation with a video demonstration of our application, which will give some insights on the backend and frontend integration as well as data storage and retrieval in Neo4j. To start with, it is pretty evident that there is an exponential increase in the amount of data that is generated today. To accommodate this humongous amount of data, relational database management system has to be expanded vertically. This is quite expensive as compared to any NoSQL database that expands horizontally. Neo4j is one such NoSQL database. It is a graph database developed by Neo Technology. It is purely developed in Java and thus provides cross-platform accessibility. It adheres to the ACID properties of a database management system. That is, all its transactions are atomic, it maintains database consistency, it isolates queries, and provides durability in times of crashes. Coming to how data is stored in the Neo4j, as shown in the figure, we have taken a movie database which we also use for our application. As we can see, the elliptical shapes are the nodes in the graph database, which are the basic building blocks of any graph database that are made up of properties, which are stored as key value pairs. Relationships are another basic building blocks of graph databases. They are also called as connectors or edges. They are used to connect two nodes. They are depicted as directed arrows from one node to another, defining the relationship between them. Lastly, the graph database uses labels, which is a name given to a set of nodes or relationships used to form a group of nodes or relationships, respectively. Moving on to query processing, it is one of the main aspects of a database management system. Neo4j uses Cypher query language. It is a declarative query language providing effective graph query expression and graph store update. The basic structure for Cypher query language is inspired from traditional structured query language. Most of the clauses such as where clause, order by, they are all similar to structured query language. Graph reading is done using clauses such as match, return, where, etc. Match clause, it is the simplest way to get data from a graph. Return clause is used to fetch the desired result from the database. Where clause is used to fetch result based on a certain condition. In the given example, this query matches all the actors with age less than 30 and return their names and age. To update any graph that is already generated in Neo4j, we use the following clauses. The create clause. It will create a node and relationship with the specific properties as shown in the example. This query creates an actor node with first name as Leonardo and age as 40. Similarly, delete will delete the relationship or node. The deletion of a single node is done as shown in the figure. This query matches the actor node with first name as Leonardo and deletes it. We can use set to add values to the properties and add labels to the nodes. We can use remove to remove the values or labels. In the given example, we set the last name of the node actor whose first name is Leonardo. Merge. Merge is used to match existing nodes or create new nodes or patterns.
Now let's talk about query optimization. Any query execution can be broken down into smaller parts by using operators. Any execution plan is a pattern consisting of multiple operators connected together. Every operator has some statistics associated with it, like the number of rows that the operator produces and this is available only if the query is profiled. Uh, it can also produce estimated rows. If Neo4j is using a cost-based compiler, we can see the estimated number of rows that will be produced by the operator. The compiler uses this estimate to choose a suitable execution plan. Each operator will ask Neo4j storage engine to do work such as retrieving or updating data. A database hit is an abstract unit of this storage engine. There are two different strategies that can be used for execution planning. The first one is the rules strategy, in which the planner doesn't account for any of the statistics related to the nodes, but just follows a set of rules. There's the second, that is a cost-based strategy, in which the statistics for every nodes are considered by the planner while evaluating the cost for each execution plan. Hence, this approach ensures the least costly plan is selected. There is also an advanced version of query profiling for query optimization that can be used for manual query optimization. Let's look at how indexing works in Neo4j. In the earlier versions of Neo4j, it operated without any indexing. It later on introduced the manual indexing, which could be written and exploited using the Java API. The recent version has introduced the schema indexing technique, in which labels are used in the specification of indexes and for defining constraints on the graph. The graph schema comprises of both indexes and constraints. So there are mainly two types of indexes that can be defined. The first one is a single property index. Uh, a single property index is the one that is defined as single property, as the name suggests, for any label. And as you can see, the create index example is shown, where index is created on the name of the node actor. This single property index can be used in equality searches, for which the example is shown. The As we have created an index on actor name, actors the name of actor property name, we can use it to search Leonardo in our graph database. We can also drop this single property index by using drop index on actor name. So the second type of index is the composite property index, and it is when there is more than one property used to create an index. Uh, the example for creating a composite index with name and gender is shown. We can use composite property index in equality searches as well, as shown in the example, where the property name and gender is used to search an actor. Uh, Composite indexes do not support queries as of now in Neo4js, which have predicates like exists or range queries, or that have predicates like starts with, ends with, and contains. Um, we do not need to mention which index to be used in a query, as Cypher will realize which index to use. If we want to force Cypher to use some specific index, then we can use hints. Constraints are another part of the Neo4j schema. Uh, in general, for any database, constraints are used to enforce integrity and prevent unauthorized access or manipulation. Um, any create query in Neo4j would create a new node, irrespective of it being a duplicate of an existing record. So we can use a unique node property constraint to avoid duplicate node creation by using assert movie.name is unique. Um, the second type of constraint in Neo4j that is available is the relationship property constraint. Uh, It is used to create a constraint that makes sure that all relationships with a certain type have a certain property. And to create a node key or a node property constraint, ensuring that all nodes with a particular label have a set of defined properties whose combined value is unique and where all properties in the set are present. We can see that the example for the relationship property constraint and the node property constraint are given as shown. Moving to transaction management in Neo4j. Um, so transactions are generally, as we know, they are atomic units of work, and they're comprised and in Neo4j they're comprised of one or multiple cipher statement executions. Uh, any update query, it will either completely succeed or fail entirely. There is no partial success. So we know that Neo4j follows asset properties. Cipher creates a new transaction if there is no existing transaction in the running context, and it will commit after the query finishes its execution. But if there is already a transaction present, then Cipher will not create a new one, and the query to be run will run inside this current transaction. The Neo4j comprises of three types of transactions. The first one is the auto commit transaction. Uh, the auto commit transaction is immediately acknowledged by the network, and it cannot be automatically replayed if it fails. The second type of transaction is the transaction function, which is preferred by Neo4j as the container for transactions. It will provide a clear separation of the database queries and the application logic. The last transaction is the lengthy version of transaction functions, which is known as explicit transaction. It is used to provide access to operations like begin, commit, and rollback.
So we're going to demonstrate the application right now. So we the app the data consists of four types of nodes: movie node, actor node, director node, and the genre node. We are not gonna demonstrate the director node, and we're using indexes on the actor node and the movie node over here. So for the recommendation part, we have indexes on the movie title. So and we are also using genre to determine the recommendations. As you can see, we can see once we get the recommendations, we can see the top five recommendations. So every title over here is indexed, and all the indexes are created before the application is deployed. And to the next part, for adding the comment over here, it's we're creating new nodes over here without any indexing. So the only purpose of this is to demonstrate our ability to add new data. So we're gonna add the movie name. Forest. So you can see we generate a unique ID. So this ID is unique for all the nodes. So we cannot have a movie with the ID 129828890. and it's system generated, so it's not under our control. Now, to remove the comment, like we can, it's as simple as giving a select query. Instead of returning something, we specify what values we want to delete. So over here, we are using the same example where we are like searching for all the comments for the movie, and we're gonna delete all those comments. And we're gonna So for Kevin Bacon number, we're using composite indexes to speed up our search, and we gonna use a multiple hop multiple path query. So the path, our output can have a path of 2 to 4 nodes. So over here we're gonna use Tom Hanks and Lou Reed. We can see like since the Lou Reed is a musician and Tom Hanks is an actor, like they're not directly related, and we have a difference. Yes, mainly over here for the application, the main focus was to display how querying works and how indexing speed ups the operation. We weren't really concerned with man- managing dynamic data. So the main most of the applications for graph database involve finding patterns in things like proteins or chemical structures. So most of that data is going to be static, so we aren't really concerned about adding new data over here.